Semiconductor research and development. Semiconductor research and development plays a foundational role in powering innovation, enabling the future, and transforming global technology. It begins with the creation and integration of advanced materials, new compounds and engineered structures designed to enhance transistor performance, increase efficiency, and enable scaling beyond traditional nodes. These materials are essential for pushing the boundaries of Moore's law. AI and computing are transforming chip design and system architecture. Through AI-driven design automation, optimization, and predictive modeling, development cycles are accelerated and performance is enhanced. These innovations impact every industry, from consumer electronics to space technology. In manufacturing, research drives improvements in process precision, yield, and reliability. Whether it's EUV lithography or atomic-scale deposition, advancements translate to better, faster, and more sustainable production. Finally, future tech focuses on quantum computing, neuromorphic chips, and beyond silicon alternatives. This frontier of innovation continues to shape the digital age. What are semiconductors? Semiconductors are unique materials that can either conduct electricity or block it, depending on the surrounding conditions. This controllability sets them apart from traditional conductors like copper and aluminum, which always allow electricity to flow freely, and insulators like rubber and glass, which resist electrical flow almost entirely. Semiconductors like silicon and germanium fall in the middle. They have variable conductivity. Their electrical behavior can be manipulated, making them ideal for digital switches and amplifiers. This variability in conductivity is influenced by temperature and applied voltage. Temperature sensitivity means a semiconductor's conductivity changes with heat, which is crucial in sensor applications. Voltage control allows devices like transistors to function as switches or signal amplifiers. These two properties form the basis for modern electronics, enabling precise control over how and when current flows through a circuit. That's the power of semiconductors. What are semiconductors? Semiconductors operate through a fascinating principle: the movement of electrons and the resulting holes in a silicon crystal structure. Electrons, when excited by voltage or heat, move through the lattice, leaving behind positively charged holes. This dynamic flow of charge enables the control of current, essential for switching and amplification in electronic devices. The most common materials used in semiconductors include silicon, which makes up about 95% of all chips due to its abundance and favorable electrical properties. Germanium is used in high-performance, specialized applications such as infrared optics and some transistors. Gallium arsenide, another key material, is favored for high-frequency performance and is often used in LEDs and radio frequency devices. Semiconductors matter because they're at the heart of modern technology, from smartphones and computers to vehicles and smart homes. Their ability to enable intelligent, connected systems makes them indispensable in today's digital world. The importance of semiconductors. Semiconductors are vital to the global economy and the backbone of modern digital infrastructure. In 2024, the semiconductor market is projected to reach $628 billion, showing an impressive 19.1% growth. This surge is driven by the fact that 95% of modern electronic devices rely on semiconductors to function. Modern chips now contain over 1 trillion transistors, enabling powerful computation and connectivity. The industry also provides over 5 million direct jobs worldwide, supporting a vast and highly skilled workforce. These devices are essential to critical applications, including mobile phones with 6.8 billion users, the automotive sector valued at $65 billion, and data centers (data), which are booming due to AI demands. In healthcare, semiconductors save lives through advanced diagnostics and monitoring. In energy, they enable smart grids, and in defense, they support national security. Economically, they have a 4.7x GDP multiplier, fueling $2.3 trillion in enabled industries. The importance of semiconductors. Market growth trajectory. The semiconductor industry has demonstrated a strong growth trajectory over recent years, with market size rising from around $450 billion in 2020 to a projected $750 billion by 2025. Despite slight dips in 2022 and 2023, the overall trend shows robust recovery and acceleration. This growth is driven by several emerging technologies that increasingly rely on high-performance semiconductor solutions. AI and machine learning lead the way with a projected 25% growth in 2025, driven by demand for computing power in data centers, autonomous systems, and generative AI. Electric vehicles, growing at 20%, require advanced chips for power management, battery control, and autonomous driving features. 5G infrastructure, with 18% growth, fuels global connectivity and edge computing. Lastly, IoT devices, expanding by 15%, connect smart homes, factories, and cities, relying on compact, energy-efficient semiconductors to function. Current R&D landscape. The global semiconductor industry is investing heavily in research and development, with more than $85 billion spent annually as of 2024. This tremendous R&D effort supports continued innovation, especially in advanced process nodes. One of the most significant milestones is the readiness of 3-nanometer process technology, marking a major leap in chip performance and energy efficiency. Over 15 major global players are driving this innovation, pushing boundaries in logic, memory, and AI chip development. Asia continues to dominate as a manufacturing hub, holding 40% of the market share, led by nations like Taiwan and South Korea. Key industry leaders include TSMC, with a 54% market share, Samsung as a memory leader, Intel known for x86 architecture, and NVIDIA leading in AI chip development. R&D investment trends from 2020 to 2024 show steady growth, climbing from under $70 to over $85, highlighting sustained commitment to innovation. Hot research areas and global R&D programs. The semiconductor R&D landscape is being shaped by several high-priority research areas. AI and machine learning chips are considered hot topics as companies race to develop specialized processors optimized for artificial intelligence workloads. Quantum computing is emerging as a next-generation paradigm, with the potential to transform computational capabilities. Meanwhile, advanced process nodes, particularly 2 nanometers and beyond, are classified as critical for future manufacturing. Power efficiency also remains vital, focusing on low-power, high-performance chip designs that meet the energy demands of modern applications. On the global stage, major national programs are fueling innovation. The U.S. CHIPS Act provides $52 billion in funding. Europe's CHIPS Act offers $43 billion in investment. China's National IC Fund is in its third phase, with $47 billion committed. In terms of R&D intensity, Asia leads by investing 18.5% of revenue, followed by the U.S. at 16.2% and Europe at 14.8%. Emerging technologies in semiconductor R&D. Semiconductor R&D is advancing rapidly with a focus on key emerging technologies that promise to redefine future computing. The AI chip market alone is projected to reach $150 billion by 2025, driven by explosive growth in artificial intelligence applications and machine learning algorithms. In quantum computing, IBM's roadmap includes the development of systems with over 1,000 quantum qubits, an essential milestone for making quantum computation practical at scale. Another major focus is the next generation of process technology, expected to emerge between 2025 and 2026, which will further reduce transistor size and enhance chip performance. Simultaneously, achieving greater power efficiency is a top objective. The industry has set a target goal of 70% power reduction in future chip designs, a vital step in enabling energy-efficient computing for everything from mobile devices to data centers. These innovations will define the next era of semiconductor breakthroughs. Breakthrough technologies in semiconductor R&D. Several breakthrough technologies are reshaping semiconductor R&D, each at different stages of maturity. AI and neural chips are currently hot, with about 90% market readiness. These include tensor processing units, TPUs, neural processing units, NPUs, and edge AI solutions, optimized for handling AI workloads efficiently. Quantum computing is considered a future technology, with only 25% market readiness. Developments in qubits and cryogenic quantum processors are progressing steadily. Neuromorphic computing, inspired by the human brain, is still in R&D with 40% readiness. It leverages spiking neural networks and memristors for advanced computational efficiency. New materials such as gallium nitride, GaN, and graphene are emerging as alternatives to silicon, with 60% readiness, offering advantages in power efficiency and speed. The innovation timeline highlights key stages. From 2025 to 2026, we expect the rollout of 2-nanometer process technology and advanced AI chips. By 2027-2028, we anticipate quantum advantage and neuromorphic breakthroughs. From 2029 to 2030, commercial quantum computing and 1-nanometer research will take center stage. Focus areas and challenges in emerging semiconductor R&D. R&D investment in semiconductors is strategically divided across key areas. AI chips receive the largest share, followed by investments in quantum computing, process technologies, and new materials. This focus aims to accelerate innovation in computing performance, energy efficiency, and scalability. However, several technical challenges remain. First, physical limits are becoming a major constraint as devices approach the atomic scale, making further miniaturization increasingly difficult. Power efficiency is also a concern, with heat dissipation becoming a limiting factor in dense chip designs. Additionally, manufacturing cost is rising steeply due to the exponential complexity of advanced nodes. Despite these challenges, the potential for breakthroughs is enormous. Quantum speed could increase by 100 times, AI performance could improve by 1,000 times, power savings may reach 90%, and chip density could improve tenfold. Leading this innovation are NVIDIA in AI chips, IBM in quantum computing, and Intel in neuromorphic technologies. Manufacturing innovations. Advanced semiconductor fabrication has reached a pivotal point with the adoption of EUV, or extreme ultraviolet lithography. At the core of this technology is a 13.5 nanometer wavelength light, which enables unprecedented precision in patterning features at the atomic scale. This extreme precision is vital for creating advanced nodes that push the limits of Moore's law. The tool enabling this capability is the ASML TwinScan EUV machine, which comes with a staggering cost of over $200 million per unit. This reflects not just its technological sophistication, but also the complexity of the ecosystem that supports it. Currently, the industry leader in EUV node production is TSMC, with its N3 process node, a 3-nanometer technology that sets the benchmark in both density and performance. To meet production standards at this level, the yield target for these advanced nodes is set at an extraordinary 99.9%, ensuring cost-effective scaling and consistent chip quality. Process node evolution. Semiconductor manufacturing continues to evolve rapidly, with each process node bringing new materials, structures, and lithography capabilities. The upcoming 2-nanometer process, targeted for 2025 to 2026, represents the next leap in device miniaturization. It will implement gate-all-around GAA transistor structures, a significant shift from FinFETs, offering better electrostatic control and performance. Accompanying this will be the use of high-NA EUV lithography, utilizing a 0.55 numerical aperture lens system to improve resolution and enable even tighter patterning. While still labeled as future technology, development is accelerating. The 3-nanometer process is already in active production. It enhances FinFET designs and incorporates EUV multi-patterning with over 14 layers to achieve critical dimensions. Meanwhile, the 5 nanometer process is considered mature, using traditional FinFETs and EUV for key layers. These advancements offer clear benefits: a 70% increase in density, a 15% boost in performance, and a 30% reduction in power consumption, enabling more efficient and powerful semiconductor devices. EUV lithography. Extreme ultraviolet, EUV. Lithography represents a major breakthrough in advanced semiconductor manufacturing. Operating at a wavelength of just 13.5 nanometers, EUV allows for exceptional resolution and precision. This technology enables the printing of sub-10 nanometer features, with placement accuracy within plus or minus 1 nanometer, critical for creating the dense, high-performance transistors needed for today's most advanced chips. EUV delivers significant manufacturing benefits. First, it reduces the number of layers required by up to 50%, eliminating many complex multi-patterning steps. Second, it enhances pattern fidelity, improving accuracy by as much as 90% compared to previous methods. Third, it speeds up processing by 30%, simplifying the workflow and reducing total cycle time. Finally, EUV improves yields by 15%, cutting down on defects and boosting overall manufacturing efficiency. These combined advantages make EUV indispensable for pushing the limits of Moore's Law and enabling the 3 nanometer and future 2 nanometer nodes. Critical equipment. At the heart of EUV lithography is ASML, the sole supplier of EUV systems globally, effectively holding a 100% monopoly. The current generation, the TwinScan NXE, supports leading-edge manufacturing, while the high-NA EUV system is anticipated to begin deployment around 2025, providing even greater resolution and precision. These systems are critical for enabling sub-3 nanometer nodes and pushing the industry toward 2 nanometer and beyond. However, significant challenges remain. Cost scaling is a major concern, with EUV tools costing over $200 million, making capital investment a limiting factor. Power density is another bottleneck, as heat dissipation becomes more difficult at advanced nodes. Quantum effects introduce atomic scale behavior that can disrupt transistor operation. Material limits are also pressing. Silicon may no longer suffice, and alternative materials are needed. Despite these hurdles, progress continues. Manufacturing success is measured by throughput at 125 wafers per hour, overlay precision of plus or minus 0.5 nanometers, equipment uptime of 95%, and achieving a 99% yield target, all of which are critical to sustaining advanced node production. Applications across industries. Semiconductor innovations are transforming multiple industries, with automotive and medical sectors experiencing particularly high impact. The automotive chip market is projected to reach $85 billion by 2025, driven largely by the rapid growth of electric vehicles. EVs require advanced power management systems, with key components including battery management systems, BMS, inverters for power conversion, microcontroller units, MCUs, for motor control, and sensors for safety systems. This sector is growing at an impressive 25% year over year. In contrast, the medical device industry, though smaller at $12 billion, plays a critical role in precision healthcare and continues to grow at a steady 8% annually. Semiconductors are essential in enabling high-performance imaging tools like MRI and CT, health monitoring wearables, life-saving implants such as pacemakers and stents, and diagnostic lab-on-chip platforms. Together, these sectors illustrate the expanding reach of semiconductor technology into essential and high-growth markets that shape our daily lives. Applications across industries. AI is transforming industries through emerging and expanding applications. In autonomous driving, AI processing systems are enabling smarter, safer navigation. This includes LiDAR, which provides 3D perception to detect surroundings in real time, and radar for precise object detection under various conditions. AI chips play a crucial role in decision-making by processing large data volumes rapidly, while V2X technology enables vehicles to communicate with everything from traffic signals to other cars. This sector is still emerging but growing quickly. Meanwhile, telemedicine is expanding through AI. Remote healthcare now relies on 5G connectivity for ultra-low latency communication, enabling near-instant interaction between patients and doctors. Edge computing allows real-time analysis directly at the source, while AI diagnostics improve pattern recognition in scans and medical data. IoT sensors provide continuous monitoring, crucial for patient safety and proactive care. Key innovations powering these industries include SiC power modules, offering 95% efficiency in energy use, and edge AI processing, enabling real-time decentralized intelligence. Finally, market distribution shows AI applications across automotive, healthcare, consumer tech, industrial, and other sectors, highlighting the widespread and growing impact of AI-driven technologies. Innovation impact. Technological innovation is reshaping industries not just in capability, but in performance and dependability. A major outcome of these innovations is a significant boost in energy efficiency. Through advanced hardware such as SiC power modules and optimized AI algorithms, systems now achieve up to 50% improvement in energy use. This directly reduces operational costs and supports environmental sustainability by lowering carbon footprints across sectors like automotive, healthcare, and industrial automation. Equally critical is the advancement in safety standards. As industries adopt intelligent systems and automated decision-making, maintaining reliability becomes essential. New technologies have achieved a 99.999% reliability rate, setting benchmarks for trust and performance. This level of dependability ensures that systems can operate continuously without failure, vital in applications such as autonomous vehicles and remote healthcare monitoring. Together, these innovation impacts, improved efficiency, and rigorous safety form the foundation for scalable, sustainable, and trustworthy deployment of AI across industries. They reflect how far we've come and point to what's possible when cutting-edge technology is engineered with both performance and responsibility in mind. Challenges and future outlook. As the semiconductor industry evolves, so do its obstacles and possibilities. Over the next decade, more than $1 trillion in R&D investment will be required to fuel growth and innovation. By 2030, many experts anticipate achieving quantum advantage, where quantum computing begins to outperform classical systems in key applications. However, as we push technology further, we're approaching the 1 nanometer physical limit for silicon-based devices, which introduces extreme complexity in manufacturing and design. Despite these hurdles, the industry is still on track for 15% annual growth through 2030. Among the current challenges, physics limitations pose a critical barrier. Moore's law is slowing due to issues like quantum effects, leakage current, and heat density, each making continued miniaturization harder and more expensive. These constraints require a fundamental shift in material and device strategy. That brings us to the future opportunities. The transition to a beyond silicon era marks a major breakthrough. This includes exploring new materials like graphene, carbon nanotubes, CNTs, 3V compounds, and 2D materials, all of which promise superior performance at the nanoscale. These emerging solutions offer a path forward, beyond the limits of traditional silicon, and will shape the next generation of electronic systems. Challenges and future outlook. As semiconductor technology advances, cost escalation becomes a major concern. The cost of fabricating at smaller nodes, such as 10 nanometers, has increased by over 300%, due to the complexity of lithography, process steps, and equipment. This rapid rise in capital expenditure is unsustainable for many players, making collaboration and efficiency more important than ever. Another critical issue is supply chain risk, driven by geopolitical tensions. Global dependencies in material sourcing and fragile trade relations mean that disruptions, such as export controls or shipping delays, can cripple production. Managing these risks is essential for maintaining resilience and securing long-term innovation. Looking ahead, promising technologies offer hope. Quantum computing is an emerging breakthrough, offering 10,000 times the potential speed-up over classical computing. Powered by superconducting or photonic architectures, this could revolutionize fields like cryptography and materials discovery. Another exciting direction is neuromorphic computing, brain-inspired architecture designed for ultra-low power operation. It holds the promise of being 1,000 times more energy efficient than traditional systems, making it ideal for real-time AI in edge devices. Together, these innovations could define the future of computing if we can overcome the challenges that lie in the way. Key takeaways and future impact. The semiconductor industry is poised for transformative growth, with a 2024 market size projected at $627 billion, reflecting a strong 19% growth rate. By 2030, we anticipate entering the quantum era, a pivotal moment that will redefine computational capabilities. Over the next decade, AI performance is expected to increase by as much as 1,000 times, driving innovations across industries. However, this trajectory depends on sustained R&D investment exceeding $1 trillion, which will fund the development of new technologies and overcome current limitations. In terms of technology evolution, we are entering the beyond silicon era, where new materials like graphene, quantum, and photonic systems will drive the next wave of breakthroughs. In parallel, a manufacturing revolution is underway, fueled by EUV lithography and 3D integration, pushing process nodes down to 1 nanometer. On the market impact side, automotive transformation is a major driver, with electric vehicles and autonomous driving contributing to a 25% year-over-year growth rate. Simultaneously, healthcare innovation, powered by precision medicine and AI diagnostics, is expanding rapidly, surpassing $12 billion in market size. These takeaways highlight a future shaped by innovation, cross-sector impact, and strategic investment, laying the groundwork for the next era of technological leadership. Key takeaways and future impact. AI and connectivity are reshaping the future, with semiconductors at the core of this transformation. One emerging area is AI-driven design, powered by neuromorphic computing. This brain-inspired architecture delivers 1,000 times better energy efficiency, opening the door for ultra-efficient edge AI applications. It mimics how the human brain processes information, offering speed and adaptability with significantly reduced power demands. Meanwhile, global connectivity is accelerating through 5G, 6GE, and the rapid expansion of the Internet of Things. By 2030, the number of connected devices is projected to surpass $75 billion, requiring robust semiconductor infrastructure to support seamless real-time data exchange across the globe. At the heart of this transformation is the message, "The future is semiconductor-driven." This future includes 3 pillars: innovation acceleration, through quantum leaps in computing power; sustainable computing, with energy-efficient solutions that reduce carbon impact; and human-centric design, ensuring that technology continues to serve people and society. Ultimately, it's semiconductor R&D that will shape tomorrow's world, driving breakthroughs, connecting humanity, and ensuring that future technologies are fast, efficient, and centered around human needs.